In this video, we will look at an aspect of calculus, optimization. So we've been given a problem. It states that a sheet of cardboard, 240 units by 150 units, has square edges of x units cut out. The edges are then folded up so as to form a box x units high without a lid. Find x so that the volume of the box is a maximum, and hence find the maximum volume. Let's illustrate this graphically. So there's a sheet of cardboard and it has sides of 240 units by 150 units, and then edges, square edges of x units are cut out. So effectively, the sheet of cardboard looks something like this. Then we said that the length of the cardboard sheet was 240 units. Now a portion of the side has been cut out. So if this is x and that is x, and this was 240, now it's 240 minus this x and minus x, so it becomes 240 minus 2x. And then the other side, the width of the cardboard sheet, it was 150 units. And then we cut out side of x units and another portion of x units, so it becomes 150 minus 2x. Then the edges of the box are folded up and we end up with a box. Doesn't have a lid, and the height of the box is x units. The length of the box is 240 minus 2x, and the width of the box is, or the breadth of the box is 150 minus 2x. Now we can move on to the next part. We need to formulate an expression for the volume of the box. Now, volume of a box is of a rectangular box is length times breadth times height. The length of this box is 240 minus 2x, and the breadth is 150 minus 2x, and the height is x units. We can simplify that, and it becomes can further simplify it so that it becomes 4x cubed plus minus 780x squared plus 36,000x. And now we have an expression for the volume of the box in terms of x. This is a cubic function, and it looks something like this. And this is a turning point, and this is a turning point, or it's also called a stationary point, and it's a maximum value at this one and a minimum value at this one. I've drawn it like this because the coefficient of x cubed is a positive number, so the shape of the cubic function is like that. Now, if we find the derivative of the function, which is the gradient of the function at any point, if we find the derivative, let's find the derivative, and the gradient at a turning point is 0. Okay, so if we equate the derivative to 0, we can find the value of x at these turning points. Now you can simplify this and work it out, but you will get the value of x is equal to 30 or x is equal to 100. So there are two x values. We need to determine which of these x values are the minimum and which is the maximum. We need the maximum value. To do this, we look at the graph. If this is just a rough drawing of what this cubic function looks like, and if we try and plot the points, we've got x is equal to 30 or x is equal to 100 for the turning points. Now 30 should go over there and 100 should be at that point, because 30 is naturally before 100. And this is a maximum value, and this is a minimum value according to the graph. So we can say that the maximum value for the dimensions of the box would be for x to be 30. Now the next part of the question says find x so that the volume of the box is a maximum, and hence find the maximum volume. We have found x. We have found the maximum value of x. And we need to substitute this value of x back into our expression for volume so that we can find the maximum volume of the box. Now I'm just gonna erase everything for a bit of space. And this is our original expression for volume in terms of x. Now we've established that x is equal to 30. That's our maximum value. So we can substitute this 30 in for all the x's, and that looks like this. And if we simplify that, we get a value of 486,000 units. It should be units cubed. So we have determined the maximum value for x and the maximum volume of the box. Thank you.